Okay, we're going to get started. Good morning, everyone. Thank you very much for attending our webinar this week. My name is McKenzie Woodman. I'm the Remote Sensing Application Specialist here at Spectral Evolution. And today we're going to be going over an indicative study in nitrogen quantification in soils. So we're going to be talking about determination of soil nitrogen content using UV-VIS-NIR spectroscopy and an overview of chemometric modeling. So to start, I'm going to talk a little bit about Spectral Evolution. Spectral Evolution is the leading manufacturer of high-quality UV-VIS-NIR spectrometers and spectroradiometers. We have full range, which we identify as 350 to 2500 nanometers, as well as some shorter wave range instruments as well. We were established in 2004, and we're located in the Boston area in Haverhill, Massachusetts. And our primary applications are in hyperspectral applications, remote sensing and vegetation, mining and geology, as well as photonics and calibration transfer. So chemometrics can run the range of different applications in each of these spheres, but nitrogen quantification is primarily used for soil sciences, soil research, and precision agriculture. So what is a spectrometer? A spectrometer, in order to understand a spectrometer, it measures light. So I'll start by explaining what spectroscopy is and how a spectrometer works. Spectroscopy is the study of the electromagnetic spectrum as emitted or reflected by various materials. The electromagnetic spectrum is a representation of electromagnetic radiation, and they're defined by their wavelength. So a reflectance measurement directly relates to the materials and chemical structures and bonds of the material that's being scanned. Our spectrometers typically have a range of 350 to 2500 nanometers, as mentioned before. So that's targeting the UV-VIS, the NIR, and the NIR range. So this kind of reflectance measurement is primarily targeting all sorts of different materials, and we're able to identify those materials based on the absorption features. So those absorption features can tell us about the chemical bonds that are present and the chemical structures. So how to choose a spectrometer? Our instruments are divvied up primarily by their spectral resolution. So we have this range of different instruments. We have the RS-3500, which is 2.7, which is our comparable to other instruments on the market today. Then we have the step up from that is the NaturaSpec and the NaturaSpec Plus. That has a 2.7, 5.5, and 5.8 nanometer resolution with full width half max resolution. And then we have the NaturaSpec Ultra, which is unrivaled in spectral resolution for field-based spectrometers and spectroradiometers. So that one would have a 1.5 nanometer resolution, 3 and 3.8 across that range. So inside of our high spectral resolution instruments, we have for the UV-VIS, we have a 1024 element UV enhanced silica array. In SWIR 1, we have a 512 element thermoelectrically cooled in-gas array. And then for SWIR 2, we have a 512 element thermoelectrically cooled extended in-gas array. So that's the specs that are inside the instrument. The NaturaSpec is our most common instrument, and this year we've launched our NaturaSpec Plus, which is the same resolution as the NaturaSpec, but has a smaller form factor, an integrated battery, and compatibility with a sensor probe, which will give you additional metadata within your data collection. So first I'll talk about some of the problems surrounding soil research. Traditional soil sampling methods are both slow and expensive, and they require collecting, transporting, and analyzing samples in a lab. So that limits how often and how widely we can measure soil health. As a result, there's very few locations, even across the United States, that have detailed and accurate soil maps. At the same time, concerns are increasing. We need more efficient and sustainable agricultural practices, and we're facing challenges like climate change, over-fertilization, erosion, and pollution. So that's where spectrometers would come in as a field-based instrument. They allow us to rapidly and accurately measure soil properties right in the field, helping build better soil databases, monitor changes over time, and guide smarter land management decisions and more targeted harvest dates for precision agriculture. So there's a few different methods for the lab-based nitrogen quantification. So the Kjeldahl method, a traditional laboratory technique, it measures total nitrogen by digesting the sample in acid and converting nitrogen compounds into ammonia. This is accurate, but time-consuming and requires a chemical procedure in a lab. And then there's the Dumas method, which is also very common, which is a faster combustion-based technique that measures nitrogen gas released when a sample is burned. Also very highly accurate, but it still needs lab instruments and controlled conditions. So these data processes can be very accurate, but they can also be costly and time-consuming, which can slow down or limit the amount of data that you can do. So later on in this presentation, we'll talk a little bit about how we built the model, and these are the kinds of methods that are used to build your test or build your model based on lab data, and then we can then extrapolate those percentages based on reflectance scans in the field. So while these methods provide a benchmark for accuracy, field spectroscopy estimates greatly expand the efficiency, enabling real-time nitrogen mapping and better fertilizer management. So here we can see one of our highest resolution instrument, the NaturaSpec Ultra, in the field. And so this is the kind of setup that you would work with. So you'd have your left hand with your ruggedized field tablet and the right hand being your contact probe, and you're able to very easily and very quickly scan large areas of soil. So in this case, we'd be measuring topsoil, but you can also use an auger to homogenize the sample and scan with depth into soil as soil changes with depth. But this is the general setup. We have this field portable backpack. The batteries are located underneath the instrument inside that backpack, and the fiber comes over your shoulder for ease of use. So, and with each scan, these typically take under 10 seconds per scan, and these can be averaging 30 to 40 averaging time. So you can perpetuate large sample sizes in a short amount of time in the field. So when we talk about spectral signatures, we're referring to how materials reflect or absorb light across different wavelengths. So 350 to 2500 nanometers is what you would use for soil science. So every material has its own unique spectral pattern. So using our UV-VIS-NIR spectrometers, we can measure how soil reflects across this full range. The shape of those reflectance curves gives us a lot of information about what's in the soil. For example, we can detect differences in mineral composition, organic matter, clay content, moisture, iron form and amount, as well as salinity and even particle size distribution. So Spectrometers let you see into the soil and capture its chemical and physical characteristics just from light. So with the same data that you collect in the field, you wouldn't just have to use it for nitrogen, you can use it for mineral analysis as well as some carbon quantification. So with the same scans. So you can get a lot of information out of these scans back in the lab after you've done your field collection. So at the molecular level, each type of bond in a material vibrates and absorbs light energy at very specific wavelengths. These vibrations occur when the bond absorbs light with a specific energy quantum. That energy quantum is directly related to frequency and inversely related to wavelength. For example, around 2200 nanometers, we can detect an absorption for the aluminum hydroxyl bonds, which are key to identifying different clay minerals in soil. So identifying, we've had a webinar on identifying different clay minerals in soil. And so I would recommend going to look at that for how these absorption features can be indicative of different fine mineral analysis. By analyzing these kinds of absorption features, we can reveal a detailed picture of soil health, fertility, and help inform better food production and land conservation and sustainable development practices. So when estimating nitrogen in soils using a spectrometer, we focus on specific wavelength regions where nitrogen-containing compounds absorb light most strongly. So these nitrogen-sensitive bands are primarily found in the shortwave infrared or SWIR region, which covers roughly 1400 to 2500 nanometers. So some key wavelengths include 1480, 1650, 1744, 2170, and 2390 nanometers. These bands are associated with molecular vibration bonds found in organic matter, proteins, and other nitrogen-bearing compounds. So by analyzing reflectance behaviors in those regions, we can build accurate models and training sets based on those absorption features, and then use those to extrapolate the quantity of nitrogen in the field. So this benefit, it allows for speed and precision in estimation of soil properties like nitrogen content. And it can be used in the field or in the lab. So if you have soil samples from past research, you'll be able to bring those into the lab and scan them under lab conditions. And you can measure effects of climate change, increase impact of fertilizers in the soil. You can do soil mapping, which is hugely important right now, as there's been a big effort to increase the amount of soil mapping and other critical land changes, and there's no sample destruction with this kind of analysis. So soil mapping, I'll just go on a tangent a little bit right here. Soil mapping is hugely important because soil can be very different in different areas. So being able to create quickly a soil library for different regions that you know what kind of soils are going to be there and be able to match with spectral analysis in real time in the field will allow you to create these soil maps a lot quicker. So the first thing you would do is create a library for a region, and then you can send out a person with the spectrometer mapping the area in real time. This would greatly increase the speed at which you can create these and accuracy these soil maps. So instead of optically identifying these soils, you can actually have lab-based data in the field identifying what kind of soil it is. So it's been hugely helpful to expand soil mapping efforts. So now I'll talk a little bit about chemometrics and multivariate analysis. So now that we've talked about spectroscopy, the next step is understanding how that spectral data can be put into meaningful form. which is where chemometrics comes in. So chemometrics applies mathematical and statistical methods to link our spectral measurements like the full range analysis to the actual chemical and physical properties of the soil. So to do this, we use multivariate analysis, which looks at many measurements across many samples at once. This allows us to detect relationships and patterns that wouldn't be visible by looking at a single variable alone. So essentially, what multivariate analysis helps us model how different soil characteristics, such as organic matter, minerals, and moisture, interact and influence each other, making it a fundamental part of building an accurate soil prediction model. And in this case, we're going to use it for nitrogen. The first thing we do is collect reference samples and prep those reference samples. And then we move on to the data acquisition, which would be scanning the samples, so the soils with different amounts of nitrogen. Then we'll do some pre-processing on the data and exploratory data analysis. We'll build a model from a training set, so those reference samples, so known samples with different amounts of nitrogen. And then we can build a model and validate that model based on that training set. So then once we have that model built, we can then attach that to any new scans that are happening and get an answer based on the model in real time in the field. So first, step one was prepare the calibration set to get a representation set of samples with, we selected a range of diverse nitrogen percents to optimize the homogeneous nature of the soil. We used a mortar and pestle to grind everything together so you're not getting any heterogeneity within the soil. And so what we did is use topsoil and some nitrogen, and then built the model that way. And it's important to note that the more data that you use to build your model, the more accurate that your model is going to be. And if you're building a model for a certain soil type, you should be using samples that are within that soil type. If you have a vastly different kind of soil, the model may not perform the same way as what you were able to see in different areas. So it's important to constantly be checking your model to see its performance with some lab data. But it's also important to note that you won't have to be using as much lab data as if you were just using lab data to do the soil analysis. So next step is build models using the PLS tool. So the X input would be the spectral data, and the Y input would be the known concentrations of that spectral data. So choose the appropriate model, which in this case would be the partial least square regression. And for this analysis, we use the eigenvector tool. So that's a statistical analysis tool that we highly recommend and is integrated into Darwin. So you choose the appropriate partial least square regression, and then perform pre-processing, which eliminates outlier and noise removal, normalization and derivative analysis for smoothing, and then cross-validation to estimate the performance of the model. So this is a view of what eigenvector looks like. So once the calibration model is built, the next important step is validation, making sure the model performs well on data it hasn't seen before. So in this case, we set aside 20% of the samples from the calibration data set specifically for validation. This ensures we're testing the model's ability to predict independent data. During model development, we use cross-validation, which provides the root mean standard error of cross-validation, or RMS ECV. This tells us how stable and consistent the model is when tested internally. Then when we apply the model to the validation samples, we calculate the root mean standard error of prediction and the coefficient of determination, or R squared. These metrics show how accurate and reliable the model's predictions are for new samples. The lower the RMSEP and the higher the R squared, the better the model's performance. So it's important to understand how well your model is working when doing this. So our experimental procedure was weight in urea or soil, and we estimated 0.5 to 11% nitrogen content range. It's also important that if you're building a model, you want to run training samples that run the range of your estimated nitrogen percent. So you don't want to have a model that's built on 0.5 to 11% and then have soils that have 30% nitrogen. It won't accurately be able to predict outside of the range. So we first used topsoil with a known nitrogen content and then added urea from Sigma Aldrich. And then we're able to quantify the nitrogen percent based on adding those together. So then we ground the samples with a mortar and pestle to homogenize them, and then split the samples into a calibration set and a validation set. And then we acquired the reflectance spectra using a NaturaSpec Ultra, as you can see here, and build the model with PLS toolbox in eigenvector, and then optimized it using with the validation samples. So this is a rudimentary, very straightforward way of building a nitrogen model. There are some more complicated ways of doing this, but this is probably the most common way to do it. And we only used 10 samples, but you can use, or for a robust analysis, you should be using about 100, or it should be a lot more than 10 samples. And it's up to you how many samples you want to use, but the more you use, the more accurate. And the higher resolution instrument that you use for these kinds of analysis, the better their performance on the actual nitrogen content should be. So, and that's because with higher resolution, you should be getting closer to the real reflectance and not smoothing anything out based on that full width half max spectral resolution. So here you can see some of the data. So this is what our data looks like after you scan it. So this is reflectance percent data. So here we're using a contact probe. This is before we do anything to the data to smooth it out. But in this, and then on the right, you can see how we scan the soil. Now here you can see where those bands or absorption features are actually located. And so as you can see, some of these features are very subtle. So you have the nitrogen bands that are relevant to nitrogen, and you have those soil bands that have absorption features based on the soil. And as you can see, those features are in different locations, which allows us to estimate nitrogen independent of the soil bands. So as you can see, some of these are very subtle features, which is why using some pre-processing will allow us to get a better agreement with a model. So what we've done is normalize the data. That makes sure that all of the scans are on a level playing field. And then we use first derivative to accentuate those subtle features, and again, to eliminate any kind of noise and things like that, anything that's affecting all of the data uniformly. And then we use mean center for pre-processing methods. So this is what the data will look like after you've done the pre-processing. And as you can see, these look very different from one another, but in the first step, they look almost identical despite the different nitrogen contents. So this is how our PLS model graphs for our statistical analysis. So you can see our calibration set and our validation set here. And then all of those different performance variables are reported there as well. And then once that model has been built, that's when you can start to see the integration into Darwin. So nitrogen quantification models can be ported into Darwin from eigenvector to estimate nitrogen percent in real time. So as you scan, you'll have another window open that will be giving you an estimated nitrogen percent, and that will log for you while you're in the field and while you're going to different locations and based on those samples. So that's a hugely important tool that we have integrated into Darwin to increase the performance and increase the amount of scans that or data that you can actually acquire in a field day. So in conclusion, accurately estimating nitrogen is one of the most critical aspects of soil research and precision agriculture. Nitrogen drives plant growth, affects yield, and plays a major role in nutrient cycling, but it's also one of the most dynamic and difficult elements to measure efficiently in the field. By using UV-VIS-NIR spectroscopy, we have a powerful, non-destructive solution that allows us to study multiple soil properties in situ in real time. This technology can capture detailed spectral signatures that correspond to nitrogen content, organic matter, moisture, and other key soil characteristics. So when we combine this basic model building steps and solid understanding of how to identify spectral features, we can create reliable models to estimate nitrogen and other attributes. Ultimately, these spectroscopy and chemometric approaches make soil monitoring faster, more accessible, and more scalable for large targets like farms or soil fields or forests. And environmental managers with this data can make better and more sustainable decisions in the future. So thank you very much for listening to our webinar this week. I was happy to share some of the key concepts in this soil analysis and how to build models and things like that. So I'd be happy to discuss any questions that you may have, and I look forward to hearing from you in the future. Thank you very much.